Hello, I'm Austin Stoker, and I'm here to present Material Science Project 4 with Giovanni Jean. In this project, we are presented with the problem of two 1-meter bars made of aluminum and iron that are clamped together in series between two rigid walls at 20 degrees Celsius. The temperature of both of the metal bars are increased by 100 degrees Celsius, and we are tasked to find what will the final length of the iron bar and the aluminum bar be, and what will be their final stress. Before we can solve for the final length and the final stress of the two bars, we need to find the Young's modulus and the linear expansion coefficient of iron and aluminum. Those two values can be found using the engineering toolbox, where the Young's modulus of aluminum is 69 gigapascals, the Young's modulus of iron is 210 gigapascals. And the linear expansion coefficients that I found for aluminum is 23 times 10 to the negative 6th, and for iron was 12 times 10 to the negative 6th. To calculate the total stress, I used the formula shown, which combines the two linear expansion coefficient values for iron and aluminum, as well as the two Young's modulus values for iron and aluminum, as well as the change in temperature, which happens to be 100 degrees Celsius. And plugging in all of the values, the stress comes out to 181.77 megapascals. The final length of each bar was calculated in a similar fashion by using the initial length of each bar, which is 1 meter, and the change in temperature, which was 100 degrees Celsius for each bar, and then their individual linear expansion coefficient and Young's modulus, as well as the shared thermal stress value. And the aluminum bar actually would decrease in length as the iron bar will increase in length, but as the problem stated, the two bars are being rigidly held together, so the total length remains the same as 2 meters.
This simulation is where 200 particles at temperature 300 Kelvin, and we're just going to see how they move. By using the stopwatch and scale function, we're able to see that on the right side. Also, from the data function, that there's 109 blue particles at an average temperature of 386 Kelvin. All right, now we're going to do the same simulation, but now with 100 particles, but still at the same temperature. Let's see what happens. We can see it's way slower. Now we're going to do a third simulation, still with 200 particles, and now with a different initial temperature at 50 Kelvin. All right, let's watch. Got even slower. Those particles are moving to the right, yeah. I want to bring into play the diffusion flux equation, Fick's first law. Movement of particles with diffusion flux from high to low concentration is directly proportional to the particle's concentration gradient. Now let's define J as the diffusion flux, capital D is the diffusion coefficient or diffusivity, delta phi, change in concentration of the particle, delta x, change in position, and delta phi over delta h equals the concentration gradient of the particle. This little illustration is kind of showing you what I'm saying. All right, given that we have this equation, I'm going to go more into like what this means. So Fick's first law predicts a flux proportionate to the diffusion coefficient d and to the concentration gradient dc over dx. In this terms, d phi over dx. The first two experiments directly prove this. The only dependent variable were the amount of blue particles. The temperature remained the exact same. So as we decreased the amount of blue particles, it's went from 200 to 100, we see that the movement of particles also decreased. And it was significant enough that you could see it with your human eye. The more particles present, the more they bounce off each other and move. All right, this is just so I can show you guys one last time. As you can see, how many are conjugating right there versus how little are coming right there. Completely two different paces. Now we're getting to the second part of our problem, the diffusion coefficient temperature dependence. Now the equation's over here. D equals D naught to the exponential E subset A divided by RT, and the whole thing is negative. Now, right here it says that D is the diffusion coefficient, D naught is the maximal diffusion coefficient, EA is the activation energy for diffusion, T is the absolute temperature, and R is the universal gas constant. All right, knowing this, we're going to explain. Now, how does the simulation prove this? Better yet, how does the simulation relate to this? All right, when T is large, like 300 Kelvin, measured flux increases a lot compared to when T is equal to like 50 Kelvin. It's consistent with an exponential increase of D with temperature. Using test 1 and 3, the independent variable becomes temperature. That's the only thing differing from them. So this therefore proves the equation stated above. And then here's just a visual example. Let's just show you what I mean. See, let's wait for that one to catch up. There we go. Hopefully you learned something from this video. We hope to catch you in the next one.